Welcome everybody to this new session of the Chilean Probability Seminar. We have a big friend of many of us here that is coming to visit us from Bordeaux now, city of wine.
Lots of.
So he will discuss with us sharp large deviation principles for descent of random permutations.
So, thank you very much for the invitation. It's a pleasure to be back home because my home is now there, but I feel like home with all of you. So today I will present some principles about large deviation for random permutations, and this is a work in collaboration with Bercu, Michel Bonnefont, and Richou. And this is kind of something that is a continuation of something that they started. So I will talk about it. So to give you a plan about what I will talk about, I will start with I will try to be as pedagogic as possible. So I will start with random permutations, something which is construction about random permutations. After that, I will talk about some observables. The observable that I will be interested in is descents of random permutations. After that, to give you a context and to see how the results that we have fits in the large deviation literature, I will give a kind of an heuristic introduction of what is happening with large deviation principles. After that, the state of art in descent statistics. Then I will talk about descent statistics for the couple. So I will talk later which is the couple that we'll be interested in. And after that, if time permits, I will talk about the construction of a probability space that let us study the statistics of the couple. Okay? So to start, random permutation. So for me, the notation will be like pi n will be a random uniform permutation in the symmetric group of n elements that I will just enumerate from 1 to n. And just to give you an idea of the construction, if you have a family of random ID uniform 0, 1 random variables, I could do fibers. I plot each of the uniform random variables, and they will induce in the relative order a permutation. And this is something that is more general with uniform random variables because it's just needed to have a distribution that is not atomic at some point, because the variables are exchangeable. So basically, I give you the construction with uniform, but keep in mind that it could be another one for your purposes. But for me, it will be just enough to consider uniform 0, 1 random variables. And so the total number of descents in a permutation of size n will be given as so it doesn't project on the screen. So still, the total number of descents in a permutation will be. Okay, so the total number of descents in a permutation of size n, that will be a sum of n minus 1 quantities, which says if the index that follows the index that I am exploring, k equals 1, for example, I will compare it with k equals 2, and I will see if they are in a descent order. For example, for this permutation, the first one is an ascent, and the next two ones are descents. Okay, so it's kind of graphic. That's why they call them descents. So first, this is just to give an insight of what is happening. Tani proved that the number of total descents in a permutation of size n it's equal in distribution to the integer part of Sn, which is a sum of IID uniform 0, 1 random variables. And I will give you an idea of the proof. First, if I have a family of uniform 0, 1 random variables, I could define another family of random variables, which can be defined as the cumulative sum of this uniform random variable that I take from the beginning, the fractional part. Okay, so this will be just which comes after the comma, and I denote here, and it will be very important. Fractional part will be which stays above the interior part. So the proposition is that this collection that I just defined, it's an IID collection of uniform 0-1 random variables, and the proof is kind of.
Sorry. So I got lost here. So wait, so your descents were in an integer value. So the n was your descent, no?
The starting point is the descent in the index k. So basically, when you get to the last one, you can count the last one. So basically, a permutation of size n would be a maximum of n-1 descent. Okay.
So it's always integer.
It's always integer the number.
So
of
the other random, this is n. To the
is the integer part. So it's the integer part. I didn't put it here. No. Yeah, it's the integer part of the sum of uniform 0. So okay, so this proposition is kind of easy to prove. What you can do is just condition on the starting part of the sum on the cumulative part, and you can see that all the rest is uniform still. Okay, so this is something that I won't prove, but I will use it to prove the Tannis theorem. Okay, so recall that I defined from UN a collection Vn. So imagine that V1, which is U1, give us that point there. If the increment in the integer part doesn't add anything, so increment equals 0, that means that my V2 will be defined in this part, which is the red part. Okay, so basically I won't make I won't get over 1 in order to get here. So if B2 is defined with increment equals to 0, I will end up in this red part. And if B2 gives an increment equals to 1, it will finish in this blue part. And what we can see is that if B2 stopped in the red part, we will have an ascent. And if it's in the blue part, it will be a descent. So basically, increments will give us the increments in the integer part will give us the behavior of the increments in the descents, and we can do it iteratively. Okay. So that's Tannis theorem, and since we know how Sn, which is the Sn, the sum of uniform 0-1s, this random variable is well known. It's called Irwin-Hall distribution, which is a continuous distribution, which is symmetric.
Just to mention, so what you were doing is essentially you were building a bijection out of, for every number you were choosing a uniform.
Yeah.
And then you were organizing them.
Yeah.
That's
exactly that. And I just studied what happened with the increment as soon as I made the permutation draw. Okay. So okay. We know the distribution of Sn, which is this sum of uniform random variables, and this distribution is symmetric. It's completely known. We have the density and everything. So by symmetry, we could directly give the expectation of the n, not the variance. We need some computation there, but it gives us the whole. It gives us everything that we need to compute the variance. So for the distance, we have expectation and variance. And now the interesting part is what happens with some properties of this random variable dn. So since we know that dn is of order n, what happens when we divide it by n? We have something that is a law of large numbers, which is due to Friedman in the 65. So this is something that was really studied from the 60s, and there are lots of proofs of lots of theorems. And right now, the interesting part is to go to the couple. So that's the direction that I'm trying to follow. So law of large numbers, we have that the n divided by m is equal to 1/2 almost surely in the limit. And there is kind of a difficulty. I try to introduce it here because in some parts of the results that I will present, there will be a correction, which is a fractional part, and that fractional part will come from this Sn distribution that is continuous So since we studied this the behavior of this dn divided by n, and dn is integer, we need to put integer parts. There will appear some fractional parts. So it's just to give you an insight that where in the results there is a fractional corrective term that will appear in the following. There is also a central limit theorem. I could find at least 8 references for that, so I put it just at least in the chronological order that I found. So the central limit theorem says that the center divided multiplied by the square root of the variance converts to a normal random variable, and we have the description of the variance in the limit. So now I will tell you what happened, an introduction of large deviation principles. So the main idea is this is really hand wave. I just wanted to give an intuition of what is happening. So the main idea is to give an adjusted behavior of the mean of these distributions. So since I know that dn divided by n, it's converged almost surely to 1/2, I will be interested in what happens with bigger than 1/2 and smaller than 1/2. So these are kind of steps that we could follow. I expect that everyone could follow. So the probability of being bigger than x, I could compose with an increasing function. So I compose with the exponential t of the argument. After that, I applied here Markov's inequality. I still says that this is really rough because it's Markov inequality, but it gives the intuition of what is happening. So Markov inequality. After that, I try to put everything together. This is the Laplace transform of dn, which I call Ln of t. So after that, I arrange the terms, and I have something that is exponential minus n tx, and I have this quantity that appears here, that is 1/n log of the Laplace transform. After that, I could define something that is called the log Laplace transform, which is the limit of this quantity. And I will try just informally to put it where it was before as a limit. And after that, I just realized that I used a 3-parameter t, and I could optimize it over t. So to optimize over t, I will try to find the more adjusted one. So I will try to push the inequality as left as possible, if we could say it like that. So I will try to optimize it with the infimum. After that, the exponential on the inside, it will change to a supremum. This led us, this quantity here is well known in the large deviation literature, which is it is called the rate function. So I will try to put it there. Basically, I gave all the steps hand-wavily, let's say, that this quantity is smaller or equal. There's just a problem with the formality, because if you try to do the lower bound, it doesn't come from Markov inequality, but it's the idea, okay? So what we have at the end is that we have this something like this, and we would try to hope that this is tight. And the idea is to prove that this is tight in some different senses. So there is something that is called rough large deviation principles, which is trying to determine just which is the factor that goes next to the n. So basically, results are if this limit is equal to the minus the rate function. And there is another one that is sharp because it's more, it gives more information. And it consists in trying to determine a more adjusted version of this one. It's not just that there is the rate function here. We try to find what happens with the factors that goes with him. Okay, so this is called the sharp large deviation principles, and it gives obviously more information than the rough ones. So, state of the art still. In 2009, Brigmida and Suraman, they proved that there is a rough large deviation principles for the descents, and they proved that it converges to the rate function, and explicitly gave this log Laplace transform. And this needs some computation. This is something that is not.
I think I'm a bit confused with something because dn is just equal in distribution to this.
To this Sn, but
Sn.
integer part.
Okay, so my question, I think you said this, but does the integer part really make life so much more complicated?
We will see for the large deviation principles, yes. For the one
For
where
the CLT and for the no.
no, that's just correct.
But at the level of large deviations, you really
Yeah,
have to.
you see the parasite that is present. So okay, so they proved this. They gave a explicit expression for the log Laplace transform, and my collaborators they proved in 2023. So yeah, last year that they could specify a probability space where they gave that the increments of descents in that probability space could be written as a random variable that condition on the sigma algebra generated up to the n follows a Bernoulli random variable with parameter which is given just by the last descent quantity. Thanks to this, they could prove that there is a martingale, which is the natural object that appears in this context, and of course, lots of theorems that comes from the martingale side. These are not trivial results, but still there is a lot of tools to prove this kind of results. So they derive obviously a large deviation principle, as I showed before, a quadratic strong law, a law of iterative logarithm that tells you which are the boundary curves in your process, a functional CLT, so this is kind of a Brownian motion result, and of course the functional CLT gives you the description of the natural CLT as a marginal of t equal 1. And this is for me, this is the most interesting part. They gave the sharp large deviation principle, which tells you that for every x of the mean above the mean, they have the large deviation principle, and I just wanted to remark that there is this parasite fractional part that we just talked about it. And as you see, there is this rate function and another functional that appears right next to it. And here is a description with Tx, which is a fixed that is a point where the log Laplace transform in the derivative takes value x, and that defines sigma x of sigma x, which is in the second derivative evaluated at tx. So of course, I just stated these two theorems about large deviations above the mean, but if you want to go on below the mean, you can do it with a symmetric argument, because ascents plus descents, obviously it's n-1, that are all the indices that you can explore with it. We could define another permutation which will be kind of a flip of the natural permutation by doing n minus sigma I. So basically, I could traduce in sigma prime, all the ascents of sigma are descents right now. So basically, it tells me that, let me write it with a bar. So dn bar will be the distance of sigma prime. So basically, I have this equal to n-1, and this let me go from, if I studied the behavior below the mean, above the mean of the n, I could go to the behavior below the mean of the n prime, and they have an an and dn have the same distribution because this transformation is an involution. Okay, so basically I could it's enough to show the results above the mean to go below the mean.
So L was the Laplace of the limit?
The L?
Yes.
Yeah, it's the log Laplace of it's 1 over n expectation of Ln t. Do you want me to go to the slide?
No, it just was when the NNT was the Laplace transform.
It's in the limit. Okay. So we have the behavior above the mean of the below the mean. We have everything that we wanted to have large deviation principles because it's the behavior of the mean, as I said before. Right now, what we were interested in, still interested in, it's
Just one question about the results before. Is it just for this I mean, if you think about it as just as a sum of uniforms but with integral path, is it for any law they want, or this is just work for uniform?
do you mean uniform random variables? These results are obtained with the help of Sn, and Sn is just work with the uniform random variable.
Okay, so they cannot obtain this as a generalization of the sum of n IID.
No, and we are working something like that. I will talk about it at the end. Okay. So yeah, there is something that comes from the behavior of a sum of independent random variables, and we will see afterwards that I will talk about it after. So what we are interested in is if I have pi n a uniform random variable in Sn, we could define the distance of the inverse of this permutation, and obviously, if Pn is a uniform random variable in Sn, P minus 1 n, it will be also a uniform random variable in Sn. So it's obvious that Dn prime it has the same distribution as Dn. So what's the behavior of the pair right now, the couple? So first result that gives some intuition, the covariance of both of the when we studied the covariance of Dn and Dn prime, we have an explicit expression. And as you see in the result, we usually renormalize by square root of n. So you see that they should independize at the limit. Okay. So theorem of Bercu, I suppose that it's called like that. The joint CLT, it says, well, if you apply the same idea as the CLT in one dimension, but you when you take two coordinates, that will converge with a normal bivariate normal random variable, which has the identity and the diagonal because they independize from the other. And what we did was basically inspired from what they did in 23. We constructed a probability space that let us study right now this pair, and to formalize all the things that they have for martingales and also for our large deviation principle. And basically this was a bar that were blocking us a long time. So if how much time do we have left?
Like 30 minutes.
Okay.
A little bit more.
I think that I will have time. So the probability space let us prove the generalization of the one-dimensional versions. So quadratic external law, law of iterative logarithm, functional CLT, and obviously this one with the marginal still recovers the Bercu theorem. And sharp large deviation principles. So
here's for the Brownian motion.
Sorry.
You have divided by t squared. Is it not like?
Yeah, it's like t squared.
Is it big T or is it small t? So no, it looks
And this is the transpose because it's this is a vector. So this is
okay. So it's not a Brownian
T.
motion. No, you are correct.
No, it's a Gaussian process with this mapping. It's not exactly a random.
And the other one was also not a Brownian motion.
No.
I didn't realize.
Okay, sorry. So we have these results, and what can we say about the sharp large deviation principle? Here I hide some.
It's very different from our problem.
Yeah, it's very different from other.
And of course, if you didn't have the integer part, you would have a problem.
I expect that this is why it's weird.
Or am I getting something wrong? Otherwise, it's just sum of independent variables. There's some.
It should be very.
Yeah, because it explodes. It's counterintuitive for me that it explodes at 0.
I will go back to that afterwards because I haven't thought about it.
Like this thing gets stuck for a bit somehow. It's just surprising to me at least. So different.
Yes. Let's talk about it later. Or-
Yeah, no, I'm not asking anything.
Okay. So for the Charlotte deviation principle that we have is here you can ask for the question with both bigger, one bigger and the other smaller, and both of the four possible combinations of them. It seems they have the same distribution and the inverse of the inverse is the direct one. We have this description like right here, so we can give the behavior of the pair when they are both above, and there is another correction term that appears here, which is the tx ty. Still, the tx and the sigmas are defined as before, and there is a little difference. Well, the previous theorem that I showed about Charlotte deviation principles, it was divided by n. Here, I put something under the carpet. There is an n-1, and this comes from asymmetry in the Laplace transform when you divide by n-1 and not with n in the couple. So that's why the n-1 correction goes there. And you have, when you study both above, you have this correction of them, both below, same correction term, but when you interchange, when you have below and above, you have minus the same correction term. We have this, and as a corollary, we have a rough large deviation principle for dn divided by n, dn prime divided by n, and the good rate function, as you can see here, it appears here, and it independizes, it separates from both files. Okay, so we have that, and there is this was kind of impressive for us because when we were studying this one, we realized that we have more tools than the Charlotte deviation principle that they had before. So basically, we could prove an improved version of this, and it's basically the full description of any order. So here I put Charlotte deviation principle of any order. It's basically because you can develop the order 1 term in P up to the P order, let's say. So basically, what we realize is that for any P, there is a sequence that such that for n large enough, we can give the description of this where these coefficients could be explicitly computed. For example, dn1, these are disgusting. We couldn't do any better to express them. So basically, these expressions are in function of the derivatives of higher order derivatives of the log Laplace transform that we spoke before. And to show you a little bit what we did, I will try to explain you how we constructed the probability space. So imagine that you have a permutation of size n. What I will do to create one of size n plus 1, it's that I will shrink my permutation and I will put it in the box 0, 1, 0, 1. This will induce a grid, let's say. And after that, I will just throw a point, uniform 0, 1, 0, 1, and I will see in which cell of these boxes it's strong. If it is strong in a cell, it will push the other ones to make room in order to define another permutation. Okay, so basically any point that goes in this box, it will create this random this permutation of size n plus 1. Okay, so this representation, let us study what happens with the increments, the number of cells that gives prescribed increments of the descents in the direct permutation and in the inverse permutation, where the increments could belong to 0, 1. So all the results that I will show here are in some sense deterministic. This uniform random variable is just to create the next one, okay? And this is something that we were trying to find this for kind of a long time. And we test with lots of simulations, and the probabilities were exact number of cells. And that was the kind of the discovery that was, we were kind of shocked. So let me define CAB if I have increment A in the direct permutation and increment B in the inverse permutation. So first theorem, every permutation pi of n out of the n plus 1 square cells has exactly this number of cells with prescribed increments, where here I put the direct and the inverse. So we will go step by step, because to start, I define for a given permutation a fiber, which will be the horizontal strip, and I will count how many of those cells in that strip give for the direct permutation increment 1 and increment 0. And this is our first lemma, and it says that there are exactly those numbers for each fiber. Okay, so how do we prove that? And this is something that is that I like a lot. It's really graphical. So what we do? So imagine that you have your permutation, and I will do the following construction. From each point, like this, I will color yellow the top left point, the top left cells up to the left of this point, and blue the bottom ones to the right. Okay, so basically, if I apply this principle and I have this permutation, I will have a coloring like this. And in some cells, since this one induced yellows to the left and this one induced blue to the right, some cells will be colored by both. Okay, so first property, each point induces for, when you see the construction like this, each point induces in every fiber either a yellow or either a blue one. Okay, so that's a first principle. Second one, now we will try to find what happens when we have for which one of those cells we have increments +1 for the descents. And here we are just studied for the direct permutation. So if we are to the left, we can't have any blue coloration, because the first point that we color is to the left, and we just color blue to the right. So in this strip, we could just have this kind of configurations. Okay, to the left, the same principle but with blue, and in the middle we could have two different situations. Either we have an ascent, and in such configuration, okay, before going there, if we are in the left, the cells that will give an increment +1 will be the ones colored by yellow, because yellow, then you connect the other one, you have a new descent. Okay, to the left, the same thing. If they are blue, they create that descent, and the other ones, they don't create that descent. Okay, so in both boundaries, we have the description of the descents created by points thrown in those cells. Now, in the middle part, we have two different behaviors. So in the interior, I wrote here, there are two cases depending on if there were a descent or an ascent. So we are kind of studying the fibers here, not in the boundaries. If there was an ascent, something like this, there is a new descent induced by the cell if they are exclusively yellow or exclusively blue. So basically, if I put a point here, recall that this is an ascent. If I put something like here, there will be a new descent and an ascent as before, so increment +1. And right now, if in this part in the interior, I have a descent, I will have something like this. Which one will have increment +1? It will be the cells that are colored both yellow and blue, okay, at the same time. Is it clear? Are there questions? Okay, so thanks to both of these properties, we could give a proof about the lemma, which states that there are prescribed numbers of cells for each fiber. So I put yellow if the cell number like this, they are yellow. So these are indicator functions of yellow or blue. Okay. Here I sum if the cell in the fiber is yellow for the left boundary, for the right boundary. If there is an ascent, if it is yellow or blue, and they couldn't be anything with both colors. So this is at the same time there is just one which values 1. And if there is a descent, I have where they are both yellow and blue, and I have a -1 to write the right indicator function. So when I have this, right now, what I can do is rearrange the terms, and this -1 appears just when in the position there is a descent. So this one counts the number of descents. So I isolate that term, and the other ones will give me the yellow ones to the left of a point and the blue ones to the right of a point. And I already said that each point induces one yellow or one blue in a fiber. So basically this sum, when I rearrange the terms, is equal to n, because one of those two is 1 and the other is 0, vice versa. So basically this one is equal to n, and I have n minus bn. So I proved this with this, and the complement obviously gives me the increment 0. Okay? So we proved that, and this gives us that this is a corollary for every permutation out of right now I see all the whole box, not just fibers. It gives me a corollary that this is n+1 because I am summing over all the fibers. Okay, so it's the number of cells with increment 1 for the direct permutation, and I'm summing over all the fibers. And this gives also the probability space that they constructed for their martingale. So this was a first confirmation. Now, for the proof of the theorem, this one. First stage is a claim. The claim is that it's enough to prove it for C11. Okay? And I will show you how we can deduce from C11 the other ones. So, it's enough to prove that C11 is equal to this quantity. First of all, we recover C00 from C11. The idea of the construction is to do this, and this inverts the ascents with descents for the primal and from the direct permutation and for the inverse permutation. So basically, if one has C11, we have 0, 0. Okay, so that's the first step. And the second one is to say, well, now if I sum the increments 0 on the inverse and 1 on the inverse, I have all the cells with increment 1 on the direct permutation. So this let me deduce the other ones from C11. So basically, I'm just interested here to prove C11 is equal to this quantity here. Okay? And the idea to prove for C11 is induction. N equals 1 is the identity, which is really easy to check. And the inductive step, there is a lot like coming forward, going backward in these proofs, but the idea is to isolate the last element that is in a permutation of size n+1. So what we do to apply induction, we will take out this. We will shrink the cells in order to induce a permutation of size n. And in this one, we could apply all the properties that we have before. And it will let us explore what happens with C11. And as a matter of fact, the gray cells that injects in some sense when we deconstruct this permutation, we mark this cell in order to have an injection. So the gray ones will remain invariant as increments in the direct and in the inverse permutation. Okay, so we have to keep track of these fibers. Okay, so I will just give you the intuition of what happens, because there are 4 cases and it depends on the increments that C star has. Okay, and this is the part when the lemmas that I just showed have some interest. So imagine that I have a C star that has increment 0, 1. Okay, so basically I explore this cell. What happened when I put a point here? It will create it will make some room to define a permutation, and I will try to keep track of the cells here that induce increments of the direct and the inverse, and also here. Okay, so if I just want to, if from pi n, so this is a representation of my permutation of size n that was induced by this one. If I try to keep track of which were the cells that creates increment +1 from the direct, this is from the inverse permutation, and this is for the direct permutation. Okay, so it has increment 0, 1 because it's colored pink, meaning that it's increment 1 for the inverse, 0 because the blue part doesn't intersect this one. Okay. Now, if I expand what happens with Pn + 1, I discover this kind of situation when I colored pink and blue, violet. The ones who has increment for the inverse and for the prime, so for the direct one. And this is where the lemma takes part, because I could inject pink cells in some sense of this cell. I could inject it with cells which are here and here. So as you see, there is a correspondence between those ones. And right now I want to study what happens with these ones that were added. And this is where I use that in each fiber there is exactly, in this permutation, in each fiber, right now I apply the property for the fibers, but for the inverse permutation. So here I have an exact counting of which ones were increment +1 for the inverse permutation. And when I follow them here, I'm kind of reconstructing this whole fiber, but here. And this led me to deduce that basically if you do the computations, the increments, and all the stuff, it let us follow the track of these increments. So this is just to give you the idea of the proof. But the preceding lemma about fibers, it was really a good step because we needed to. So was everything that I wanted to say. Thank you very much.
Thank you very much.
Many thanks. Really good and pretty.
Thank you very much.
No, it was wonderful. I know two things. This allowed you to construct a bivariate martingale.
Yeah.
Okay.
Yeah, because the procedure that they had before, it was not to study the procedure that they had before is not to throw a point in all these boxes. It was just make the increments 1 at the end.
Yeah.
They just added at the end. But since when you put points in the middle, it disarrange everything. The problem was that, and in order to follow exact countings on this part, that was the part when the would be varied.
So it could be a very market. So it's considered it must be Browning in some sense. The behavior must be close to Browning. But no, let me put you another question more.
Mhm.
I don't know if I understand very well these things, but or permutation. But if you consider you pick a random pair,
Yeah.
and now you consider the distance of sigma, you have a good law.
Mhm.
And now if you construct
Ah.
sigma square,
Can it be written as a sum of both coordinates?
or sigma square or sigma cube or the computation, what happened with this with this?
The problem is that the construction of tanning, he created the next permutation in this fiber again. So just at the end, and when you try to mix for both coordinates, you can keep track of what happens with the interior part of the direct and the inverse. So that was the problem. We found a representation, but it's one random variable condition to the other. It's Bernoulli. It's a twisted one, and it didn't let us like explore more properties about it.
Okay, many thanks.
So I was wondering what happened with all the patents. So you said
Ah.
last on this and what do you
Okay.
think? Something like that?
As Avelio remarked, Sn can be written as a sum of uniform random variables. So the question was, is it intrinsic that these properties hold when UK is uniform? And the answer is we are live. So if you put uniform random variables there, and the answer is no, we are trying to explore what happens with another observable permutations. Here I will write, which is so distance are just defined like this up to n-1. Okay. But there is another observable that it's kind of interesting in the random permutation literature, which is called the major index, which is the average when I multiply this where the index gives a descent. So it's the sum of it's the mean of the positions in that descent. This random variable could be written also as a sum of uniform but uniform discrete random variables. So this is equal to distribution to n-1 of, let me call it UK bar, where UK bar, it's distributed as a uniform random variable, but on the indexes. Okay, UK up to K. Okay, so there is still a sum, but right now the distribution of the elements in the sum is different. They are not IID, they are just independent, and they can be written as uniform and discrete uniform. We could give basically all the results that we have for distance for the major index. There is not a lot of literature in the major index. Last year, they have also a chart large deviation principle. And but we're still on the way to prove more things about it. Like, if I'm not wrong, we unblocked the part of the chart deviation for every P, and we are trying to see what happens with the couple, but this is more intricate. So your question, but we couldn't give exactly a principle. If you have a sum of random variables, we couldn't state like a proper universal here because it really depends. And we try to find in the literature which ones could be written as such sums.
So let's say that you have, talking about alternative observables, let's say that you have some subset S of the numbers from 1 to n minus 1.
Mhm.
And now you care only about the descents in which the difference of the two numbers belongs to S. For example, let's say that S is all the numbers from 2 to n minus 1, and you don't care about the descents
On
of
the
the
last
next one, but only of the larger ones. Do you have something about the distribution of this on the word?
I think that you can construct twisted ones that couldn't be explored. I imagine that the one that you just said could be reduced in some sense. It has solved the intuition. Yeah, but because you have the partial sum up to one less. But still, if you have a subset of the indices and you want just to explore a sub-permutation that is induced by the huge permutation, you could have something that is kind of different. Here you need to have uniform random permutations. If you bias the loss of the things that you are studying, I don't think that it fits really, really well. Like biased random permutations, I don't know. I don't really know. But it depends. You can be really creative to to define other ones, and usually it gets out of this kind of results.
So I have two. So one is I inspired by Servet. So do you have the joint law of the descent between sigma and sigma square? Would you have sigma and sigma minus 1? You have the joint law?
Yeah.
Sigma and sigma square?
I don't think that I could give an answer, a straight answer to that.
And then I can ask, maybe that should have been the last one. I don't understand something about the technique, but something is waiting in my head. So if you take n uniform points taken in the square,
Yeah.
this induces
A random permutation of
a
size n.
uniform random permutation. If you take another point of that one, so you take another uniform point that also induces a
Yeah.
uniform one.
So basically,
that's
for the
not exact. That's not that.
this one.
Yeah, that is not that one.
Yeah.
Why both of them work? So in a way, so somehow it is really weird for me. This is what they have done at the beginning.
I also thought about this question, and the problem is that it's not that it's not the same, but the computations become really like twisted in some sense. The good thing about fixing for a permutation of size n against the points, the uniform 0, 1 points in the square, is that the areas here are kind of prescribed, but the computation says that a certain permutation will appear still with the same probability when you have the uniform points.
So here
But-
somehow you have more the joint law is somehow easier to understand.
The general is easy to understand because the boxes are of prescribed size.
But there is a computation that allows you to say this is uniform. This is what was bothering you.
Yeah.
So it's not completely direct.
It's not completely direct, but in order to make it grow step by step, it helps you to have boxes of size n plus 1 1 over n plus 1 squared.
Yo tengo una pregunta.
Okay, Chen.
Ya, por quien quiera una pregunta en online.
Hola, hi Luis, how are you?
Hola.
¿Quién pregunta? ¿Yo? ¿O?
Pregunta.
Dale, Joaquín.
Gracias. ¿Qué tal, Luis? En English. Sí, perdona que no pude ir presencialmente, pero aquí estoy. Yeah, no, that wasn't the question. That was a comment, a side comment. No, yeah, you mentioned, and I was about to ask, but Avelio also already asked, I think, that you can write something in terms of an empirical mean, no? But I cannot see what exactly the expression is. You wrote it on the whiteboard, but I cannot see it clearly.
How should I do it?
Yeah, I could not change the
size.
size. So maybe you can read it slowly.
So
No, or just say the.
I will just show you the.
Okay.
So basically here in the Tannis theorem,
Okay.
have in some sense that you have a sum of random variables.
Mm-hmm.
And what happens if you try to apply the same techniques with a sum which has different random variables inside? If I could generalize that, and the point is that we couldn't state that general theorem, but we apply it to another observables that are interesting in the random permutation literature.
Mm-hmm.
So the point is that we also proved something with the major index, which is the mean of the position of the descents, if I took like orally. But when we tried to state a general principle, we saw that we should fix some hypotheses that make it like lose generality, and it's more a proof of concept that we give because it could be replicated for other sums, and we show another an application with another kind of sums. But yeah, it kind of we really wanted to give a general theorem, but we found some obstructions to try to put it like general. Even if
Because
I tried to give a general principle but it didn't apply to the major index.
Okay. No, because my question was in the sense that since you haven't large deviations for the empirical measure, even not only empirical means, I don't know if what the things that you're interested in cannot be written in terms of some nice function of the empirical measure, because in that case you have the contraction principle and maybe you can get things, but probably it's not better than what you did, very likely. But yeah, that was the question. If you cannot draw information from the fact that what you're counting depends on the configuration of points at the end, and then you have a large law of large numbers, let's say, large deviation principle, and sometimes you can draw information from the observables, let's say, or whatever continuous function from the empirical measure in this case.
You have not spoken about the observables, you say.
At the end, I just said that I wanted to speak about another observable, and this was the major index. I haven't thought about anything about the empirical measure. I think that results here could be translated in that sense, but I don't see the direct obstruction in the theoretical part. Here there is kind of from the Laplace transform, basically if you know how to dominate some integrals that appear, you have basically the whole description. But the techniques in the integrals are kind of twisted, are Parseval identities. Those are things that I don't know how to translate it directly. I couldn't answer like positively or negatively directly here, but maybe there are techniques that could be inherited by the empirical measure, but should be studied separately, I think.
Okay. Okay, thank you.
Yes. So about the relationship, if any, with the Bordia earnings and URL.
Yeah, that's
this is my topic. Somehow it was.
When we started to study this, we tried to tackle the problem with the polyarms, but we didn't get to that point because we had already the result that we wanted. Bernard remarked that we could also do something with polyarms, and even the results of the rough large deviation principles in the state of the art that I presented. Some come from the polyarms and others from binary decision trees. Basically, the large deviation principles from the direct permutation, it comes from polyarms analogies and trees, observables on trees. So I don't know which is the relation with the couple, but I know that there is some coding that is interesting to explore. I think that it's some directions that I still have to explore. For the moment, we haven't tackled that kind of problem. Yeah, that's perspectives of this work.
If you see a permutation, that a transformation between two added numbers.
Okay,
That is, say to one you put 1/2, to two you put 1/2/2.
okay. So basically you make a decimal.
So you put the transformation between real number. Can you do that? And so. And something like that, no, is or no. Well, you cannot make this sort of no.
So-
It cannot work.
Like an infinite.
Yes, it cannot work. So I can say, no, I must see it. Okay. No, nothing.
Okay. I'm still thinking about it.
Okay, so you said that maybe choosing from not uniformly around on the permutation is probably impossible. If not really, really difficult. But what if you choose point with a measure on the plane? And from that you can produce a permutation.
As I said at the beginning,
So you can have a coupling of any coupling of uniform and uniform.
okay. Uniform continuous, you say?
No, take any coupling of the uniform on the units on the unit. So create a measure on the unit square by coupling to any. These are a permutation. So you choose your permutation under this any measure. Can you do the same? It seems that should.
You know that the structure of a permutation it depends on the patterns that you plot. But even the permutation, when you have uniform and uniform, you have the whole space that it's kind of dense with points. So I don't see how you can define like the limit of a permutation without any restriction of the patterns is the whole box 0101. So I don't know how you can express something. You have to avoid patterns, and as soon as you avoid patterns, you bias the law, the law, and the law is really complicated to bias. So I don't think that the techniques that we use here could be applied to the permutations with any block patterns. And even the limit figure, the limit forms are kind of prescribed, and I don't know how in these techniques you can exploit that one.
So let's try to do information. We are so we have seminar next week, same time. The seminar.